point of this part is to define analogs of the vectors I and j, covariant. Excuse me. Let's just start again. What we're going to do now is it's a slippery slope. We'll have a special video, the outtakes. All right, what we're going to do now is to extend the idea of these coordinate vectors I and j to arbitrary coordinates. So without leading you to the answer, I'll just tell you how it's done. It's done in a very beautiful way, and actually consistent with what I said with just a few minutes ago, where I said that all important objects are obtained by differentiation. So this basis, coordinate basis, which in our world we'll call the covariant basis, and the meaning of the word covariant will become apparent a little bit later on. The covariant basis, I and j will be called the covariant basis, not the coordinate basis. And it is defined the following way. So we'll do it in the case of polar coordinates, but of course it works for all coordinate systems. So polar coordinates look like this. There is an arbitrary axis. It's not the x-axis, it can be a completely arbitrary axis. So a side note now, when you're defining a coordinate system, do not define it by a reference to Cartesian coordinates. So it's very tempting to say that x is r cosine theta and y is r sine theta, or r is x squared plus y squared square root, and theta is whatever it is. It's very tempting to say that, but that requires another coordinate system to define the coordinate system you're about to use, which is not fair. It's such a vague beginning. Well, where did the coordinate system start? Where did the Cartesian coordinates come from? So each coordinate system must be defined on its own terms with just by making reference only to geometric concepts. So the way you define a polar coordinate system, you say, pick an arbitrary axis. Pick an arbitrary axis. And that's your axis where the angle is 0. And then any point is defined by two coordinates. The distance to the arbitrary origin, so that should have been the beginning. Pick an origin. Draw a straight line in an arbitrary direction. In direction of your choice. In the direction ultimately dictated by the problem you're solving. And now every point will have two coordinates. 1, the distance to the origin. 2, the angle that this line forms with the axis. Counting in the counterclockwise direction. If you count it in the clockwise direction, it'll be a different coordinate system. So the coordinates of this point are, look at that, perfect. No, 2.1 and pi over 6. That's the coordinates of this point. So again, you draw coordinate lines. The coordinate lines look like this. These are the lines of constant theta. So I missed somewhere, right? So I'll draw 3. Why did I draw 3 like this? This is theta equals 3. But why this subtle angle? This 3 is almost pi, right? So these are radians. 1, 2, 1, 0, 1, 2, 3, not quite pi, right? And then 6 will be over here. And then finally it becomes 6.28. Right, so almost full angle. Might as well complete. Is that right? No, that's not right. They all don't quite make pi. So like this and like this. Wow. All right. These are the lines of constant theta, and here's the lines of constant r. Unit. It has to somehow reference the geometric unit that existed in the space before you ever drew coordinates. So this is r equals 1. This is r equals 2. Perfect. This is a polar coordinate system. Let's define its coordinate basis. It's done in the following way. You pick an arbitrary origin. So for this I'll go to yellow. Now yellow will no longer mean coordinate system. will not mean an alternative coordinate system, not just part of the drawing. Let's define our basis at this point. So you consider the position vector R. Position vector R. R as a vector field was a perfectly well-formed notion before we introduced the coordinates. But now that we've introduced the coordinates, R becomes a function of two variables, R and theta. So now R is a function of two variables, R and theta. Or, more generally, here comes the first instance where you see new types of indices. R will be a function of our two coordinates. In particular, it could be R and theta, but generally it's Z1 and Z2. So coordinates are denoted by an upper index, superscript. That's just our notation. So now it's R and theta. When you have a function of R and theta, what can you do with it?
Differentiate.
Differentiate. So you differentiate. You find dr dr, and you find dr d theta. And that's your coordinate basis. That's your covariant basis. The most interesting part here will be drawing it. But let's define it. So it will be denoted by E sub r. E sub r will be the coordinate vector associated with R. And it's defined as dr as a function of R and theta, d theta, dr. And E sub theta, excuse me, and E sub theta is defined as dr as a function of R and theta, d theta. These are very nice definitions because they're intrinsic to the coordinate system. For any coordinate system, you could evaluate these derivatives, dr dz1 and then dr dz2, and you have a pair of vectors. So this is a rule, right? That's what's, when I made the claim that tensor calculus is actionable, that it's algorithmic, you have a rule that's the same rule in all coordinate systems. And that rule is refer the position vector to the coordinate system and evaluate the two or however many partial derivatives. And those are your coordinate vectors. That's your covariant basis. And another thing we discussed last time is that you in fact can differentiate vector quantities with respect to parameters. Yes?
Isn't that kind of a random definition?
It is.
Why a derivative?
Yeah, sure, it's a random definition. Yeah. It's a random definition, but you'll just see its usefulness. You will see these things emerging naturally. Yes. I would, at this point, I would say it's a random definition. But let's evaluate these guys. It won't take much space for the Cartesian coordinate system. Let's start there and then do the polar coordinate system. Here's my Cartesian coordinate system. I need my unit, my trusted unit. Right? Okay. Okay. Going now in this direction. Here's my Cartesian coordinates. I won't even draw the position vector itself because it doesn't matter where the arbitrary origin is, because we'll be finding differences only. You'll see in a moment that where the origin is does not at all matter. So let's figure out dr dx. So the analogous definitions will be dr dx, dr dy. R referred to the variables x and y, and differentiated once first with respect to x, that's E sub x, and then differentiated with respect to theta, that's E sub theta. So what's the definition of the derivative? So let's evaluate here dr dx. Let's see what we get. What's the limiting process in this? You take x, you change it by a small quantity, 0.1. Let's start with 0.5. you change it by 0.5, you look at the corresponding difference in the denominator, you divide one by the other, and then try to formulate what would happen if you took this to the limit. So changing x by 0.5 from this point means going from this point to this point. Does everybody agree? So we went from this physical point to this physical point. And we have to subtract r at this point. We have to subtract r at this point from this point. And so we have to subtract this r. I don't want to draw it, it'll make the drawing unnecessarily messy for no reason. From this r. And of course it's this. Is that correct? So that's the change in r. Divided by the change in x. What's the change in x? 0.5, right? Divided by the change in x, what vector do we have? Describe it with words.
Unit vector.
Yeah, it is the unit vector, because this is the vector of length 1/2. See? 1/2. You divide it by the change in x, it becomes the unit vector. So here it is for 0.5. Now let's take x equals 0.1. That means change the x variable by 0.1. It means you end up here. Find the change in r. That's that little guy whose length is 1/10. Divided by delta x. What do we get? Same vector. So it actually doesn't depend on the delta x. So in the limit, as x goes to 0, it will just be this unit vector, which is also called, what's the name that we use for this vector? I. So, Alex, this partially answers your question, right? Yes, it is a random definition, but at the very least, it recovered I. So now this I and j falls under this framework. So that's good. Right? So now I and j can be thought of as dr dx and dr dy. And if we looked at that quote-unquote yellow coordinate system, the doubled one, of course the derivative would be twice as large, and d should really be maybe called r prime, because it's a new thing. It's a function of x prime and y prime. It will be this vector. So it works. It actually works for all affine coordinate systems. And for the Helsinki coordinate system, it'll be these guys. It just works perfectly. Okay? So now, let's see what happens in the polar case. Which one do you want to do first? Let's do dr first. I'll do this in a dismissive way, claiming that we've done this before already. Okay, let's do dr, that's fine. So I will actually do it at this point, because drawing the position vector itself is messy and not helpful. Because the only thing that matters is from where you go to where you go. Let's first take delta r equals 0.5, just like we did before. So all of you think about the point, going from point r theta, if this is the point r theta, going to the point r plus 0.5 theta. Where will that point be? Describe it with words.
Just longer.
Just further out. Yeah, that's right. Further out from the origin by 0.5. So radially, you go radially out. That's what it means to change r by 0.5. You see, we're working with a coordinate system on its own terms. It's very nice. And we're getting to know the coordinate system. For instance, where do you go as coordinates change? That's how you familiarize yourself with a coordinate system. So it's this vector, so that's delta r. And when you divide this by 0.5, by the change in r, what do you end up with? The unit vector in the radial direction. And if we took r equals 0.1, just think that whole thing through. What vector would we get? Same vector. And in the limit, it'll be the same vector too. So dr, you can only describe it with words. It would be a crime to write it as cosine theta I plus sine theta j. It would be an absolute crime because it introduces a background coordinate system, which is totally contrary to the spirit of all coordinate systems being equal. So because it is a geometric object, the best you can do is describe it with words. or pictures. And in words, it's the unit vector that points in the radial direction. There you go. It's the unit vector. Well, I don't want to draw it here. No, I still can. No, I can't. Singular point. All points except that one. This is all E sub r, no longer constant. E sub r. Unit vector in the normal direction. So the coordinate base, so what characterizes affine coordinate systems is the fact that the coordinate basis is the same at all points. Here, the coordinate basis will be different at all points. Let's now look at this point and evaluate E sub theta. E sub theta. You guys all think about what E sub theta is and realize that it's a problem that you did on your last homework. Because E sub theta is the derivative of the unit vector as it rotates around parametrized by the angle. So the derivative will be the unit vector in the orthogonal direction. Remember that? Yeah, so we don't have to do this again. We don't have to approach it from the limiting process point of view. We just know this derivative. We're familiar with this derivative already. It's the unit vector in the orthogonal direction. That's on the unit circle. What about here? Think about d theta, I'm sorry, E sub theta here. What will E sub theta be at this point?
2 times.
Twice as long.
Twice as long. So you can also, you can describe its length. Its length is r. It points in the direction orthogonal to E sub r. You might also want to have to say in the counterclockwise direction. And its length is r. Perfectly geometric description. And its length is the distance to the origin. Perfectly geometric definition. You will find in a lot of physics books where this E sub theta vector is normalized to unity, which is, in my book, absolute madness. You lose these beautiful definitions, right? You have to say it's this normalized. Take something very elegant that makes it something very unattractive, and a whole lot less useful. A whole lot less useful. Okay, so this is E sub theta. So we've defined what the coordinate basis means for an arbitrary coordinate system. And it's actually not so hard to visualize because these things are orthogonal to the coordinate lines. So you can always pretty much visualize them. Just one definition before I answer your question. The angle is always 90 degrees here for polar coordinates. So coordinate systems whose covariant basis consists of orthogonal vectors is called an orthogonal coordinate system. That's the definition. Yes?
If you don't normalize it,
Yes.
and you're solving problems in different r's,
Yes.
you're going to have different coordinate systems.
Exact. Not different coordinate. Yes. Different local coordinate systems.
Right.
Yes. So it becomes a little bit of a problem. So what you're really saying is a problem is a very valid question that has a beautifully valid answer, which is coming soon enough. But you're saying that some vector with coordinates 3 and 5 here
Yeah.
will not equal to a vector with coordinates 3 and 5 here. And wrong word, components. So let me repeat that correctly now. A vector with components 3 and 5 here would be a different vector than a vector with components 3 and 5 here. Because when you say components 3 and 5, it means with respect to a basis that emerges here, this way. And it'll be a different basis from here. So you can't compare vectors by comparing their components. You can see that as a negative.
Also, it continuously changes.
It continuously changes. Even if you take a constant vector and you move it without changing the vector at all, its components will change.
Right.
That's exactly right. That's because the components of a vector are as much about the coordinate system as it is about the vector itself. That's just something to realize. You know, the takeaway right now is you can't compare vectors by comparing their components. if they're with respect to the covariant bases at different points.
But it's the same vector.
But it's the same vector. It's the same vector that has different components because different points have different bases. So, we can now define what the vector gradient is. It will be the wrong definition, just like it is in Cartesian coordinates, but at least now we have a definition, an attempted definition. An attempted definition for the gradient of f. So on the left-hand side we have something beautiful and geometric. On the right-hand side we have an attempt at defining it analytically. And you might naively write something like this, that it's df dr e sub r plus df d theta e sub theta, and you can easily convince yourself by taking scale polar coordinate systems that this just doesn't work. Not equal. So it needs to be fixed. The fix is coming pretty soon. So, but we've taken a step forward. At least we have something to put here. And we can write very generally, once again, with the word not in there, that the gradient of f equals df dz1 and this would be called e sub 1, first one, e sub 1 plus df dz2 e sub 2. This is a definition that can at the very least be evaluated in any coordinate system. So it's a positive step forward. Except it just will depend on your choice of coordinates, so it needs a little bit of a fix. But we have taken a significant step forward. We have defined the coordinate basis for any coordinates. And can at least now have expressions that need fixing. Before we didn't even have that.
Do we still have to normalize this like we did with the Cartesian one?
No, absolutely. Oh, would that work? So it would actually work for it would work in polar coordinates. That would be a fix, but not here.
Okay.
And Evan's example, not for this coordinate system. That's much more than just normalization. But here it would actually work. If you divided it by the length of e sub r squared, so in other words, by by 1, and this by r squared, that actually does work. It's amazing. And it's the same expression as it is in stretched Cartesian coordinate system. So you see where it was, growing. The range of applicability of this expression, E1 dotted with E1, that's really a better way of putting it, right? Length of E1 squared. And this is E2 dotted with E2. All right, let's call this our best attempt. This works in Cartesian. This works in stretched Cartesian. In fact, this will work in all orthogonal coordinate systems, but not this one. So we need something even better. It's yet an additional step in the right direction, just not good enough. Yes.
So if for an orthogonal coordinate system, if we're thinking of polar, is it like a local orthogonal coordinate system that
You can
just
use the word
continuously-
local orthogonal coordinate system.
that
Yes.
continuously rotates because of the relationship between your...
You can think about it that way. Rotate, well, it doesn't just rotate, and one of the vectors grows as you get further away. Right? But they always stay orthogonal to each other. Yeah. It's a very nice special coordinate system, yes.
Also, in that coordinate system is the
Polar?
E sub r, that's going to be a constant everywhere, right?
No, it's not a constant. Because here it points this way, and here it points this way.
Constant
Magnitude.
Constant in magnitude. Yeah. You have to be very precise with what you're saying. So it varies. There's no 2 points that have the same basis. No 2 points have the same basis. And the origin actually doesn't have a basis at all. The state is not defined. So it's a singular point. Okay? Let me show you one nice, if you can call it an application. You will see how was it your comment that this is a random definition? Well, now it already seems a little bit less random, right? So I'm about to show you somewhere where it just naturally appears, and you will not at all think that it's random. You'll think that it's actually very nice. Consider a curve. Consider a curve. Remember we said x is a function of, let's even use arc length, s. This is where arc length starts its count. Positive in this direction, negative in this direction. Arc length is our parameter. And we would consider x as a function of s and y as a function of s. Well, let's call this a thing of the past. Our coordinates are now z1 and z2. I'm not even saying polar, Cartesian, or something totally different altogether. Our coordinates are now z1 and z2, defined in this Euclidean space. And our curve, let's call it capital gamma. I use lowercase gamma in the book. Gamma. This is z1 as a function of s, z2 as a function of s. This could be in polar coordinates. R is a function of s, theta is a function of s. It could be in Cartesian. X is a function of x, y is a function of s, or any other. Here's the big question. It will at first seem to you completely unanswerable. And then you'll see how surprising and how simple the answer is. Here's the unit tangent. What are the components of the unit tangent with respect to the basis, with respect to the covariant basis at this point? You can't even draw the covariant basis at this point, right? Because in polar coordinates it'll be one thing, right? If this is the origin of our polar coordinate systems, then the covariant basis might look something like this. If it's some other coordinate system, then the covariant basis can look totally different. And I'm not even specifying which coordinate system we're dealing with. Maybe it's Cartesian, and the covariant basis looks like this. Maybe it's polar, maybe it's some other coordinates altogether different. So and yet we have our unit tangent, perfectly defined vector, and we're playing the same game. We have a geometric concept, and we want to find an algebraic expression for it. In other words, we want to write t as t1 e1, get used to components getting an upper index, just get used to it, plus t2 e2. We want to express t1 and t2 in terms of z1 of s and z2 of s, because this defines the curve. So everything about the curve should be expressible in terms of these equations, if you also know what coordinate system is imposed. So how do you find t1 and t2? Dot products with e1 and e2?
Yeah, like find the projection.
Yeah, but it will still involve t. It'll be t dotted with e1, t dotted with e2, and these may not be orthogonal, so you need the cross terms as well. It's all doable, but it'll be still in terms of t. We want it in terms of these equations.
It's the derivative.
Derivative? You're saying it's dz1 ds and dz2, so this is dz1 ds,
Right.
and this is dz2 ds? No chance, right? For an arbitrary coordinate system? Or is there? All right, so true to my statement, everything can be proved or derived by simple differentiation. All you have to do is write the right identity, write down the correct identity, and take the derivatives of both sides. Here's how you do it. You will be doing calculations like the one I'm about to show all the time. And it's just so satisfying to do this because you feel like an observer. A lot of the times in tensor calculus calculations, you feel like you're watching a movie. Everything's taking care of itself, and you're just watching it happen. And whatever happens is the right thing. And whatever the final answer is, it's the right answer. So here we go. What is our definition of the unit normal? Do you remember? What is the definition of the unit normal in terms of some kind of derivative? It's dr ds. So you gotta remember that it's dr ds. Should I remind you why it makes sense? Because dr ds, advance s a little bit, you'll end up here. Here's the little change in r. You take a limit, it becomes the tangential vector. And because we're using arc length as our parameter, it's the unit vector. So it's dr ds. So t, might even write as a function of arc length, is d position vector expressed as a function of the arc length. I will say it maybe a few more times. We should really use a different letter, because r denotes the position vector before there were coordinates. And r of s is a function of s that can be differentiated. So different sort of thing. But that's okay, because by writing of s, we're actually saying which one, what r means. ds. Okay. And I will write it here, but then substitute it there. But r of s can be expressed as a composite function, where you express r as a function of z1, leave some space, z2. Right? That's what we did just a moment ago when we were talking about the covariant basis. We were thinking of r as a function of the coordinates. Perfectly valid. And you substitute in there the equation for the curve. And you substitute for the curve. And now, this is the hard part, as far as I'm concerned. Writing down the identity of which you next need to take the derivative. And I will just take the derivative of this by the chain rule. It'll be dr dz1 ds plus dr dz2 ds. You guys are with me on that? Equals dr dz1 dz1 ds. Be careful. Z1 appears twice. It means two completely different things. This is Z1, the coordinate, the independent variable. This is Z1. It's this Z1. This really deserved a different letter. But then we would run out of letters and be confused. This Z1 is the equation of the curve. So this dz1 ds is the derivative of this function. So always make it very clear to yourself what the symbol means. dr dz1 ds plus dr dz2 ds. Same comment about dz2 ds. Continuing, actually we're almost done. What's dr dz1? E sub 1. You see? Covariant basis. It appeared on its own. We didn't have to force it. And so dr dz1, now I will disagree with Alex and say it's an entirely natural thing. Because look how naturally it appears in calculations. So this becomes, I'll write it in opposite order. Ooh, correction, in yellow. These are full derivatives, because z is a function of one variable only. So that's the ordinary derivative. So it becomes dz1 dz1 ds e1 plus dz2 ds e2. So indeed, you were right. This is T1, and this is T2. This is the component of the unit tangent with respect to E1, and this is the component of the unit tangent with respect to E2. Super simple calculation. You just have to write, this is the hard part. You just have to write the right identity, which requires thinking very carefully. What's a function of what? This will be the hard part. From here on, you just have to be careful, slow, and enjoy the process. And the answer will emerge on its own. So the way I will write it is that Ti, all of the components at once, equals dz1 as a function of arc length ds. There you go. Dzi as a function of arc length ds. Beautiful expression. Works in all coordinate systems. Isn't that so satisfying? You just have to evaluate these partial derivatives, and they'll have some meaning. There will be the components of the unit tangent, but with respect to what? With respect to the covariant basis. So these things always work together, the components of a vector and the covariant basis. Beautiful.